Hi, this is Charles Amaggio. Welcome back to R for Epidemiologists. I want to round out our discussion of Poisson regression by speaking a little bit about overdispersion in a Poisson model. As I mentioned, in a Poisson formulation, a Poisson model, there is an assumption that the variance is equal to the mean. So our expected values of y sub I, which in our formulation were nu, or our little offset variable, times theta sub I, should be equal to the variance as well. And then in that case, the standard deviation should be the square root of mu sub I times theta sub I. If we were to do residual analysis, then the standardized residuals of z sub I should be equal to y sub I minus y hat sub I, all divided by the standard deviation of y sub I. If we substitute through then with our Poisson formulation, then we should have y sub I, our observed values, minus our fitted values, which are mu sub I times theta sub I, divided by the standard deviation, which is the square root of mu sub I, theta sub I, all should equal our standardized residual. We can, if we wanted to, calculate a chi-square based on this, where we have the sum of all our z sub I squared compared to a chi-square distribution with n minus k degrees of freedom. And this actually leads to a second step in this, which is that the average value for a chi-squared distribution with n minus k degrees of freedom is about n minus k. This allows us to set up actually an overdispersion parameter. And this whole discussion comes from Gelman and Hill. It's really very nicely done, where we can compare the sum of our z scores over our n minus k of degrees of freedom, and we should expect it to be about 1, and we'll accept anything up till about 2. Anything beyond 2, and we'll start to consider it's overdispersed. So how then do we do this in R itself? And it's actually relatively straightforward. We'll go back to our fatalities data set that we used when we introduced Poisson regression. We'll load the fatalities data set, and as you recall, we ran a quick Poisson model where we looked at fatalities predicted by the year, state, beer tax, and with an offset variable of total vehicle miles in millions of miles. And if we wanted to, we could take a quick look at that summary here. We're not really interested in the effect of state or years. In this case, we're actually looking at beer tax here, which if we exponentiate that, we exponentiate our variables here, we see that there's about a 25% decreased risk in those states associated with a beer tax. And if we exponentiated the confidence interval for that model, wait one moment for that to come up, we'll see that it was statistically significant, or it didn't cross 1, so we believe that that's statistically significant. Now, you must evaluate overdispersion in a Poisson model. That's why I really want to go through this right here. All I've done right here is I've set up that model, that little formula that we just discussed, where I have y hat is basically our response, is our predicted variables, and there's a function in R that will extract the predicted values. It's called predict, and we're going to save them into this object called y hat. Then we're going to subtract y hat from our observed variable here, which is fatalities, and divide through by the square root of y hat, which will give us our standardized residuals. And now what we're going to do is basically compare the sum of those standardized residuals to the degrees of freedom for that standardized residual. And I stole this code directly from Gelman and Hill. They use the cat function, so it produces this little sentence for you, and it says the overdispersion ratio is 5.9. Now that's significantly beyond 2, so we're going to consider that overdispersed. What to do now? Well, there are a couple different ways you could approach it. You can actually take the square root of this value and multiply all the standard errors by that value and then recalculate things to make them appropriately narrow. Or what a lot of folks will do is run a negative binomial model. In R, the negative binomial function is found in the mass, the MASS library. So we load the mass library, and then we run the exact same model. Instead of using GLM, we use GLM negative binomial. There's just a little change here. Rather than offset equal, its offset is a function in this, and otherwise it's essentially the same model. We run that model, runs relatively quickly. Take a look at the summary of this model, and you know what? We could actually, I'm going to grab this just so that we could see the difference between the exponentiated results. This would be model NB. I'm going to grab this, put it right here, and put that here as well. Run that, waiting for that to happen here. And what we find is that it is actually, it can a little bit, but it is still statistically significant. It's actually a little bit narrower here. That's actually nice to know. We can take a look at how well our negative binomial model addressed overdispersion by running that same little bit of code again, which we do right here. And it really didn't do that great a job in actually addressing it. So I wouldn't be happy with this. In fact, it may very well be that this is just not a good model for these particular data, either Poisson or negative binomial. We may want to take another look at how we're going to model these things. But in any event, that is overdispersion and the negative binomial model.